All right, so we are beginning our next chapter called electrons. So the electrons, we're going to be talking about how the electrons are moving within our atom. We're going to start by looking at our visible spectrum because the visible spectrum occurs because of our electrons. Our visible spectrums are the colors that we see. So the visible spectrum goes from 400 to 700 nanometers. And we can see down here, we have our whole electromagnetic spectrum. It starts all the way from 10 to the negative second. It goes all the way to 10 to the fourth. And you'll kind of see what it is. So here we have gamma rays, we have X-rays are going to be here, ultraviolet. And so in between are going to be our visible spectrum. So only a small portion, so 400 to 700 nanometers, is visible to the human eye. So the X-rays, ultraviolet rays, microwaves, radars, those are all giving off wavelengths. We just can't see them. So what is a wavelength? So a wavelength is created by the movement here. And we measure a wavelength from the crest, so the peak of a crest, to the peak of another crest. So we measure from the peak of crest A to the measurement of crest B. So again, it's going to be from the peak here to the peak here. That is one wavelength. So whenever you're mentioning it, it's going to be your wavelength, and it's going to be measured, since we're talking about length, meters. Usually you'll see like nanometers, centimeters. So anything with meters is going to be a wavelength because we're talking about the length of something. So we're measuring a distance. So here we have our different waves. So here we have two different waves. So we're going to call this wave A and we'll call this wave B just so we can make some references. So again, that wavelength is from the crest of each of the waves. So we have from point A here to point B is going to be our wavelength. And down here, if we wanted to find a wavelength, we can do from this crest to this crest. And again, our symbol is going to be lambda. So that's what our lambda looks like. It looks like a wave. And again, our unit's going to be meters, nanometers, some variation of that, centimeters. So now we're going to kind of look at the other pieces of information we can obtain from a wavelength. So here we're going to have a long wavelength. So this one's going to be a long wavelength because from point A to point B is longer than down here. So point A here to point B is a lot shorter. So this is going to be a long wavelength where this will be a short wavelength. Okay, then we're going to see the words frequency and energy. So energy is going to be the amount of energy that's created from this wave, and the frequency is how quick the wave is moving. So in order to measure the wavelength or look at the wavelength, we would want to put, let's say, an imaginary wall here. And we're assuming that these are both moving at the same speed. So we're going to assume that, so then in order to measure the frequency, you're going to look at how many times the wave is going to hit this wall. So we're going to have this imaginary wall because the waves are going to move at the same speed. So here, anytime a crest hits, that's what our frequency is measured. Same thing here. So every time a crest hits, that's going to measure the frequency. So again, hitting this wall. Well, looking down here, this one would hit 4 times for every 2 times that one's going to hit. So therefore, this is going to have a high frequency. So it's going to have more waves hit the wall than this wave up here. So B is going to have a high frequency, where A is going to have a low frequency because the waves are larger, hitting the wall less often. Which means that since it's moving, or since it's less frequent, it's going to have a lower amount of energy. So these two are going to have a direct relationship. So the higher the frequency, the more energy. The lower the frequency, the lower the energy. So we have the long wavelength gives a low frequency. So these are going to be inverse, A short wavelength is going to give a high frequency. So this is also inverse. So that shorter the wavelength, the more frequent, or the higher the frequency, because the more frequently it's going to hit this imaginary wall. Again, because these are going to be moving at the same speed. Well, how are waves created? Well, waves are created by the electrons being absorbed and emitted in an atom. So in order for us to emit an electron, we'd have to add some source of energy or some sort of something to get the electron to absorb energy. So it's going to start at its ground state. So its ground state is going to be where it normally sits. So this is going to be the electron at its ground state. So we'll say ring 1, so E1. So the ground state's where it naturally is going to sit. Well, what's going to happen is, let's say, for a lab, we're going to do the flame test lab. So we're going to add heat to this atom. The electron is going to absorb, so it's going to absorb energy. And it's going to move to the next energy level. So as it's absorbing energy, it's going to move to the next energy level. Well, when it gets to that next energy level, it gets so unstable that it's going to fall back down, and it's going to emit or release energy in the form of a wavelength. So when this electron goes from the second energy back down to the first energy level, so back down to its ground state, it's going to release a wavelength. And that wavelength is where we're going to see our visible spectrum, the radio. So depending on the size of this wavelength, depends on what energy and frequency it's going to be giving off. So again, electrons always start at their ground state. They absorb energy. They jump to that next energy level, and they're unstable there, so they fall back to their ground state. As they fall back, they release what we call a photon, which is just a pocket of energy, and that energy is in the form of wavelengths. Okay, and again, the shorter the wavelength, the more energy. The longer the wavelength, the less energy. Okay, and the bigger the jump we see, which we'll go to the next one, so the bigger the jump we see, the more energy we're going to release. So looking at here, we have our ultraviolet, visible light, infrared. So we can look here, if we wanted to see the one with the most energy given off, going from 6 to 1, so falling from the 6th energy level back down to the 1st energy level, aka the ground state, we're going to give out the most energy. Meaning we're going to have the smallest wavelength. We're falling just from energy level 3 to its ground state of energy level 2. That's going to give out a small amount of energy, which means that we're going to see a long wavelength here. So the larger the jump from energy level 1, or from the energy level, the more energy that we're going to get. And you can kind of see these values down here. So here we have a very long wavelength, so this is going to be a small amount of energy. Where here we have a small wavelength, so we're going to have a large amount of energy. So we're going to go through one equation today, and then we'll go through another one tomorrow. So our first equation we're going to have is C equals lambda V, and this is going to help us calculate our wavelength in relationship to our frequency. Our C is going to be our speed of light, which is always 3.00 times 10 to the 8th. So this is going to be a constant. Never, ever, ever will this change. Since it is a constant, sig figs do not count. So no sig figs. So these sig figs there are never ever going to count because it's a constant. Our lambda is going to be wavelength. And our lambda is usually found in meters, but if we look at our constant, it needs to be plugged in. So usually we'll find it in nanometers, but because of our constant, we always have to convert this into meters. So usually we find our wavelength in nanometers because of the visible spectrum, but we always have to convert it into meters because our constant, those units need to match. Frequency is going to be V, and that's going to be hertz, so Hz, or S-1, which is the same thing as 1 over S. Okay, so hertz is the same thing as 1 over S. It's just another way of writing it. So these mean the same exact thing. Okay, so if you see hertz, you can just cross it out and put 1 over S, because we want seconds to be our denominator because of our constant. So this is our first equation, C equals lambda V. So we're going to go over a problem going through how to calculate this. So it's asking what is the wavelength of a light that has a frequency of 3.10 or 3 times 10 to the negative fourth hertz. So remember, this is the exact same thing as 1 over S. So we're doing C equals lambda V. Well, we always know C. C is always 3 times 10 to the 8th meters per second. Okay, it doesn't matter what else the problem tells us, that is always true. Okay, so again, we look back at here, this is our constant. So now we're going to look at what other variable we have. Well, we're given hertz, so we know that that's going to be our frequency. And I'm just going to change it to 1 over S to make more sense of the unit, which means that our wavelength is our unknown. So I'm just going to plug everything in. So we have our C equals lambda. We don't know our lambda, and then we know our frequency. All right, so we want to figure out our lambda, so we want to get lambda by itself. So lambda's right here. Well, with it right now, we have lambda times our frequency. So in order to get lambda by itself, we want to divide both sides by our frequency. Okay, and after we do that, our seconds are going to cancel out, which means that the only unit we're going to be left with is meters. So when we divide this out, we get 1, because we only want 1 sig fig, because those don't count. It's be 1 times 10 to the 12th meters. And that would be our final answer. We don't need to convert it to nanometers because it doesn't specify that we have to. So we can just leave it as 1 times 10 to the 12th meter. So there's another problem at the end of the video, so I want you guys to try that on your own.